Okay. So as you can infer from looking at the schedule, I'm Mike Shelley. Uh, I'm an applied mathematician from New York University from the Cron Institute, and I'm also I guess I'm called a group leader at the Flatiron Foundation, Flatiron Institute in New York, where I have a group in which Wen sits called Biophysical Modeling. Okay, so I think we're about to move from statistical physics to continuum mechanics for a bit. So this is a rough outline, I would call it provisional, of what I'll be talking about because I've only prepared my first 3 lectures, so what happens between 3 and 6 is a little complicated. But this is basically what I'll be talking about. I was asked to be fairly pedagogical in talking about some introductory material in fluid mechanics, in particular how it relates to locomotion. And most of the time, because of the relative facility with which you can manipulate the Stokes equations, I'll be talking about collective behavior in swimming in the low Reynolds number world, where actually far more is known scientifically than in the other regime of high Reynolds number. So there's, but I will talk a bit. You can see here that in day 4, which I guess is Monday, that's day 4. Oh, day 5, sorry, which is Tuesday. I'll talk about some work that we've been doing at NYU. We have a laboratory there, the Applied Mathematics Lab, that I started with Jun Zong about 20 years ago, and it's a fluid mechanics lab, an experimental lab, and we have done a lot of work in problems related to biophysical locomotion, especially at high Reynolds number. And we've been working on, with Leif Ristroff, we've been working a lot these days on collective behavior of interacting flying objects at high Reynolds number. So I'll tell you a little bit about that. People talk about schools of fish and flight, bird flocks as being examples of active matter, and there's been some interesting work on that from the point of view of Vishik type modeling. But relatively little is known about how fluid mechanics might actually participate in organizing all these things. So I'll tell you a bit about that, unless you don't want to hear about it. I'd be very disappointed if you didn't. So my disappointment is not the point of the world. And then the final talk, I'll really spend an hour and a half talking about what we're doing these days, and that has to do with active matter problems inside of the cell, things that have to do with transport of things like pronuclei inside of embryos and by microtubules and motors and all this kind of thing. And I'll also talk about work we've been doing in active materials, again, mostly focusing on microtubule motor systems. Okay. So this is just to ease our way into everything. You've all heard about the mighty Reynolds number at one time or another in your life. I'll back up and be a little more formal about stuff in a bit. But in terms of locomotion, which means I'm talking about a freely moving object which is propelling itself through a fluid in this particular case. That's what I mean, swimming or flying. The Reynolds number of the induced flow by this object moving through it is really what organizes the way you have to think about the physics of the problem. And I'll spend a bit of time talking about that. But just to set the stage, to make sure I'm sure many of you have heard these kinds of stories before, but maybe some of you have not. And I want to make sure that we're all sitting in the same place. So the Reynolds number is really just well, not really, it is a dimensionless constant that for something moving through a fluid that has a scale L and is moving with a velocity u, it measures the relative importance of inertial to viscous forces on that object. And by inertial forces here, I mean inertial forces within the fluid. And the whole issue of the inertia of the body is also another degree of freedom in the problem, which can be quite interesting, actually. And so this is the classic Euler scaling of what's called form drag. When I'm pushing an object through a high Reynolds number fluid, it's got to move all that fluid out in front of it. And this is more or less what the force takes to do that. And this is the classic low Reynolds number drag that you would see associated with Stokes's solution of pushing a sphere of radius L, scales like that. And so if you just eliminate common coefficients, you get the famous rho u L over mu. And so this Reynolds number, once you non-dimensionalize the F equals ma, the Navier-Stokes equations for a simple viscous incompressible fluid, then you just end up with a single dimensional constant, that Reynolds number multiplying what is the acceleration of a fluid parcel, which is the substantial derivative of fluid velocity du dt, being balanced by pressure and viscous forces in this dimensionless form. Okay, and so there's three interesting regimes in this world, and we'll be talking most of the time about the low Reynolds number regime, in which case I'm eliminating the inertial term, and I just have a balance between pressure and viscous forces under an incompressibility constraint. And that's the world of low Reynolds number swimming. There's a couple of bacteria happily twisting their flagella and then propelling themselves through the fluid like a little screw. And so if you write the Navier-Stokes equation in what's called the vorticity form, then so the vorticity is the curl of the velocity, it's the local, essentially up to a factor of a half, it's the local rate of rotation of fluid parcels. Then for these two bacteria, which are talking to each other somehow through the fluid, the Reynolds number is around 10 to the minus 5, and I have a quasi-static problem to determine the flow vorticity. And indeed is quasi-static for the velocity as well, if I express it through the Stokes equations. What this means is that in this type of world, communication of fluid interactions is instantaneous. It's all quasi-static. And so what that really means is that in the low Reynolds number world of Newtonian fluids, which is very special, but water is what we live with, and it's Newtonian, communication is instantaneous. That's the important thing. Unless you have other things in it like polymers that might introduce another time scale, and I'll say a little bit about that as well. Then there's the opposite end, and so that's a white ibis. I saw them down in Australia a couple of years ago. That's not my picture, but they're kind of magnificent birds. But in that case, I've cheated a little bit. Does anybody know how I've cheated here and when I wrote down d omega dt is equal to 0? See, this is a test. Who has actually taken a fluid mechanics course and remembers something important? What's that? I'm cheating. I'm acting. Sorry. That's a very canny answer, but not the one I was looking for. So that's also correct. But what this is saying is that there's a conservation law associated with vorticity. Right? It's conserved along particle paths. That's only true in 2 dimensions. Yeah, there's another term in here. This is a little more complicated in 3 dimensions, but it still expresses a conservation law. And as was just said, then that's only true when you're away from this flying object. Near the flying object, you have to, it's a singular perturbation problem. You have to account for the fact that the fluid is still stuck to this thing and it produces vorticity. And that's, of course, what gets conserved once it's advected away from the body. So here's kind of the classical picture for flow around a sphere. At low Reynolds, at 0 Reynolds number, we have this nice symmetric quasi-static problem. It doesn't really know left from right. Here I'm pushing fluid back in this direction. And that's the first expression that I've made of Stokes reversibility. Actually a very important thing for low Reynolds number swimming. I forgot to talk about him or her. I have no idea. But there's a whole other world where viscous forces and inertial forces of the fluid are in balance. And this is, obviously, you would call it intermediate Reynolds number. And it has some very interesting kinds of organisms that have to propel themselves or don't have to. They've chosen to, they've evolved to. In this kind of regime. And what you're actually seeing here is a small mollusk. It's about 1/2 centimeter in length, and it's called Cleona antarctica. And when it's small, when it's an infant mollusk, not sure what they're called, molluscina, molluscite, something, then it turns out you see this pair of wings. They don't have wings. They have bands of cilia wrapped around their bodies, actually 3 bands, and they do a power and recovery stroke like you would see around a paramecium, for example. And they propel themselves around using a classic low Reynolds number swimming strategy. But once they get large enough, they unfurl a set of wings and they start to fly around in the fluid. And this has to do with a question of scale. And so we'll talk about that a bit too. And okay, I think I covered all those things, except to say this is the regime where the vorticity that's being shed from the body or being produced at the body, let me put it differently, is kind of hanging around. Okay, it starts to be discrete in terms of having a vortical structure, but it's not quasi-static, nor is it some completely loose thing that gets shed off of the boundary layer. So it interacts very strongly with its own kind of fluid field in a particular way. Okay. And of course, up here we have turbulence and we have shedding and complicated wake structures and all these kinds of things. So I'm also going to talk a bit about, as I said, collective behavior. In fact, that's active matter. We're supposed to talk about collective stuff in the end. But here are some examples. I'll probably talk about each of these a little bit, at least, except for the one I really haven't solved yet to some degree. Well, this one I don't need to solve. So here are all kind of fluid-mediated collective behaviors. So here's a peloton in a bike race, and everybody's lined up and behind each other, and they're all drafting each other. And so the bulk of the drag goes to the leaders, moving the fluid out of the way, and then the guys sitting behind it, the people sitting behind it are taking advantage of that leader, and so they have far reduced drag. Let's see, I'll move this way. So we've all seen these kinds of movies, I think. This is actually the 3rd time I've been at Leuch, and first time I was here talking about my work in neuroscience. I used to work in kind of visual cortex modeling. That was after I had a falling out with my previous life as a free boundary problem person in fluid mechanics. Decided I wanted to do something else. I went into neuroscience. I hated neuroscience in the end. And then I came back to kind of fluid mechanics, but much more biological. And so I was here again about 8 years ago at a previous active matter meeting, which was named slightly differently, probably so, which allowed this one to get funded without any difficulties because there was no past. Okay, now I'm here again. My main memories from, I chatter a lot, but my main memories from being here are being jet lagged and preparing lectures. This is a very beautiful picture showing just a flow trace of a suspension of swimming bacteria, and these little yellow dots are the bacteria themselves. And what you see is vortices and jets and things like that are much larger than any of the single bacteria. And so that's an example, one of the most prototypical examples of an active matter system that's self-organizing to some extent. That the fluid is allowing the bacteria to organize themselves into large-scale flow structures. And I'll talk about some of the instabilities we believe that underlie the transitions to these kinds of states. That'll be part of what I talk about. Is kind of there's getting to be now kind of a set of classical instabilities of kind of fluidic active matter systems, and I'll go through some of that. It's kind of stability calculations on top of PDEs. Okay, another self-organized object is the mitotic spindle, made up of microtubules, motors, and crosslinkers of many, many types. If you pull the ingredients of this out of the cell, you purify them, as this Sonomir Dojic's group has now been doing for quite a few years. You can create kind of out-of-the-cell active matter systems that here on the surface are very dynamic, and people here, quite a few people here know quite a bit that and are quite expert at it, formation of disclination singularities and things like that. this is really what I'll talk about on the last day, which is kind of using these types of elements to do useful work inside of a cell. Getting the pronuclear complex into the right place. Of course, this is actually a single cell C. elegans embryo, as it says here, single cell C. elegans embryo. And what you're seeing here, oh, now let me ask another expert's question. What is wrong with this picture? Who's a real bench biologist in this room? Is there anyone? Oh, that would be excellent, but no. That would be really good. The problem with this is that we had to squeeze this into a PNAS article that we had written about this quite a few years ago. And we had to turn all of the microscopy photographs sideways so that the posterior sits up here and the anterior sits up here, down here. And there's a convention in biology. First of all, you never use MT as an acronym in a paper. And the second is that the posterior is always on the right and the anterior is always on the left. And we got bitter complaints from one of the referees that we had broken this sacrosanct rule. So, but anyway, what this is showing, you can't quite see this very well. See, my job here is to entertain you. We have an hour until dinner. Everybody's hungry. I'm starving. So what you have here is two nuclei. One contains the male genetic material. The other one contains the female. The upper is the male. The lower is the female. These two need to come together, combine their material, form a mitotic spindle, duplicate their chromosomes, and separate them. So you go into the first cell division. So here's where they've come together. And these star-like objects here are indeed asters, hence the word. Star-like, hence the word aster. But, and what's happening is that these are just nucleating sites of microtubules, and they are interacting with either the boundary and or the cytoplasm of the cell, force generators immersed or embedded within or upon, and moving this thing into the center of the cell where it rotates and a mitotic spindle forms. And then shortly thereafter, the chromosomes will condense out onto what's called the metaphase plate. Okay, so I'll talk about modeling and experiments of this on Wednesday. Work that my group has been doing, Dan Needleman at Harvard, for a few years now. Okay, so that's kind of the gist of the problems. And I'll come back to this slide again, except to say we're really going to start here. I want to start on this other end where far more is known, introduce you to some I'm going to try to make it mostly just useful facts for those of you that work in this area, or things that are interesting, which is sometimes independent of being useful. So, okay, so let's start there. So what I'm going to do now is I'm going to talk a little bit about continuum mechanics. I'm going to talk about Navier-Stokes, its boundary conditions, things like that. And then I'm going to move to the low Reynolds number limit and talk about the Stokes equations, which have an incredible amount of analytical structure, which is why they've been so popular as, well, as kind of the place to look. Plus, when you're in the, I should say, it's not only that, it's not just mathematicians doing this. Another reason is that things move really slowly, and that's very useful. Okay. Any questions on this thus far? Okay, let me bring the screen up then. Thank you, Shoyan. So partly this is going to be setting notation and just introducing some standard things that we need, mathematical objects we need to talk about the problems. So this is my canonical, those are waves. This is my canonical bucket of fluid, which I'll call V. It's called V naught, say. Okay, it's full of fluid. Fluid is characterized by two, actually more than two things, but I'll talk about the two that we're concerned about for the Stokes equations. One is a velocity, and I will be talking very little about two-dimensional problems. It's almost all 3D. So I will have a velocity that's defined everywhere in here. And I might use the classical UVW notation when I write it as a sequence of scalars. Or if I'm doing tensor stuff, you know, U1, U2, U3. And I will keep this notation for the next 6 lectures. Okay? And likewise, x is a spatial coordinate, x, y, z, or x1, x2, x3. Okay. Now, let's say I take some point here, x, and I take a point nearby. So I have a little displacement vector r here. Okay? And this is very trivial. And I just want to expand u around this, you know, with this small displacement vector. I'm saying it's small. Around this point x. And this is a trivial, you know, high school calculation, but it introduces you to things that we will be using notationally at least over and over again. So I can write this as u plus grad x u times r plus other terms, order mod r squared terms. Okay. Now, this is now just introducing what I use a slightly different convention for what I mean by a tensor vector multiply or matrix vector multiply. So I just want to make sure we're in the same place notationally again. And so when I write this, grad xu, I look at the ijth component. It is switched from what is a standard notation. So it's ij. And then matrix vector multiply means I multiply by rj. Okay, so there we go. So that's worth remembering, because otherwise when you start doing calculations everything will be wrong, which is inconvenient. Okay, so I have this tensor here, or matrix here, which I'm just going to write in terms of its symmetric and anti-symmetric parts. So I'll write this as u of x plus 1/2 grad xu plus grad xu transpose plus 1/2, well I should put a bracket there, grad xu minus grad xu transpose all times r. And this object we will henceforth call E. Okay? And E is standard, is one of 2 standard notations for what's called the symmetric rate of strain tensor. Because it's symmetric and because it's made from rates of strain. Okay. This, so I can say the usual things about it. Since it's symmetric, it has real eigenvalues, and all of its eigenvectors are orthogonal. Okay? So, real eigenvalues and orthogonal eigenvectors. Yeah. Okay. This guy W is called W, and it's what's often called the rotation tensor or the spin tensor. It's anti-symmetric, so all of its eigenvalues are purely imaginary. Now, I'm just writing those down because one should, right? So, so then if I were solving a problem that looked like this, R dot is E acting on R, just a simple linear dynamics. This would be what's called the dynamics of a pure strain. Okay, because the eigenvectors are orthogonal and the eigenvalues are real, I can always move to a basis in which everything is diagonal. And then I'm just talking about, if I start with a little sphere of fluid, then along directions which had positive eigenvalues, I would just extend into an ellipsoid, moving out, and directions which eigenvalues were negative, I would compress in, and it's just like that. So I start with the sphere. Then I could always put things into another frame where x, y, and z are just the directions of so-called principal vectors. And there, so here, if lambda 1 was greater than 0, I would extend out in this direction. Lambda 2 is, say, less than 0. Lambda 3 less than 0. Then I just contract along two directions, and I extend out into the other. It's just modeling that kind of dynamics. Very simple. Let's say I have R dot is equal to WR. Well, it turns out that I'm going to write this down. All right, okay. So this, it turns out, because it's an anti-symmetric matrix, it can always be written as a vector across the argument. Okay? So this is just actually 1/2 the vorticity of the vector across R. That's its action on that matrix R. And so all that's going on here is it's just taking this vector R and just spinning it in a cone around the vorticity vector. Or I should say that's what the vorticity, if you like, is doing to this displacement vector. Okay? So it's just this. And this vorticity, so it's just, here's the vorticity, here's R, and it's just spinning this guy around. And this vorticity, I'll remind you, is the curl of U. So let me just say one thing. When you're talking about dynamics of high Reynolds number fluid, vorticity is the thing. Okay, that is the fundamental object, mathematical object of how things move, because vorticity moves itself through the Biot-Savart law. So it's much different at low Reynolds number flow. It's not so convenient to use the vorticity in the same way as you do at high Reynolds number, because it's not associated with the conservation law. Okay. Okay, but these are standard kind of operations. Okay, now, oops. Where did I put my notes? There they are. Oh, yeah, one other thing is that I pace, as some of you have probably already noticed. I pace a lot while I lecture, so I lose things constantly. Okay. Now there's another field. We have a velocity, and we also have a fluid density, mass per unit volume, that gets pushed around by this velocity field. Okay? And so we can write down a conservation of mass relation that just says if I take a parcel of fluid and I label it somehow, I measure its mass and I track it through the fluid, it's not losing any mass or gaining mass. And so conservation of mass, and here I'm suppressing a whole discussion about Lagrangian and Eulerian frames, which make all this kind of fun to talk about. We have the following PDE, del rho del t plus div dot rho u is equal to 0. So that's the expression of conservation of mass. Okay? This gives me a chance just to introduce another concept, which is a substantial derivative. So I can write this as rho t plus u dot grad. Rho is minus rho div dot u. Yes. Good. Yes. No, it's not. No. Think about that. If I have a region of fluid, it's no. You have a solid body rotation is a constant. If I have a circular, yeah. Okay. Okay. So this object here, we'll often write as that, d rho dt with capital D's. And what this is the time rate of change. I hate to write it out. I feel all those hyphens in the direction of flow. Bless you. Okay, so this is just a differential object which you can interpret as a time rate of change of a scalar quantity looking in the direction in which the flow is moving. Okay, is that clear? Okay. So let's say I'm going to make life really easy now. We're only going to be interested in problems mostly, in fact it's the only kind of problem I've ever really worked on, where the density is constant. Okay, so henceforth, let rho be equal to some rho naught, which is a constant. So this d rho dt then is in 0, right? And what that means then is that the right-hand side has to be 0. So this is conservation of density of particle packets in their density is the invariant associated with that being 0. And then the divergence of u has to be 0. So I said that in a really awkward way. But anyway, what I'm trying to say, if I have a constant density flow as a constraint, then the divergence of the flow must be 0. I could have said it better. So this is what we're going to be dealing with. Always that. Constant density, divergence of u is equal to 0. Okay. How about F equals ma for a continuous material? Well, there's a kind of a nice argument again, playing around with frames of motion. You have a little packet of fluid. It has a mass, which is the integral of rho over that packet of fluid. I look at its contained momentum as it flows forward through the fluid, and I make a modeling assumption. I make the modeling assumption that the only forces that act upon that packet of fluid are body forces like gravity, and forces at the boundary that are coming from the action of the rest of the fluid outside of it pushing on it. So there's this kind of locality assumption on the way the fluid talks to each other through virtual surfaces across which it exerts stress from one side to the other. Under that assumption, Cauchy showed way back when that the form of that stress had to devolve from a scalar tensor, from a yeah, great, from a tensor. Okay, yeah, that was good. Okay, and so what this means is that the central modeling element in complex fluid mechanics, active, passive, whatever, the central modeling object is the stress tensor. Sigma of x. And so if I have a region of fluid and there's a normal, then the stress that's being produced by the outer fluid, I'll call that S, the outer fluid across the boundary into this inner packet of fluid can be expressed as the stress tensor times the normal. Okay? And what this means, and this is due to Cauchy, it's really kind of a scaling argument. What this means is that generalized momentum balance has the following form. Looks like this. This is the general F equals ma for a continuous material described by local stresses. Okay? And so here, that's the substantial derivative of the velocity field, which is simply the acceleration of a particle in the fluid. Wait, who asked something? Oh, okay, I'm sorry. I was saying with words, it's an equation for sure. But so this is the stress, the fluid. Let's give this a name. Let's call this omega. The fluid external to omega exerts at delta omega, the surface. So this is a stress which sits on, which is the shearing or the pushing or the extension of the inner fluid by the outer fluid pushing on it with the stress. It's a force per unit area. It's a stress. It's a stress. So if you look at this, this has units of force per unit volume. Okay, so this guy has units of force per unit area. I'm divvying it. That makes it a force per unit volume. Okay. Yes. Oh, of course they are. Thank you for that question. So if you have a fluid in which you are exerting no body torques, so you're not pumping any angular momentum in, like a simple fluid that doesn't have any particles that you're spinning or anything like that, the stress tensor will typically be symmetric. Things like water. So there's actually, I'm not sure why you asked that question, but there's a whole lot of very interesting active matter problems now that have to do with having particles that exert stresses on a medium. And so for example, how many of you have seen some of this work on spinny rotors by William Irvine of Chicago? Yeah, so those are kind of active matter systems where you're applying an external magnetic torque onto a particle that's immersed in the fluid, and it creates an anti-symmetric stress as a consequence. Yes? Yes, it is in the form that I've given it. But there would then be another equation, which is this equation over here, conservation of mass equation, that you would have to tag with it. Yeah, so problems that are versions of turbulent convection. For example, you have temperature-dependent densities that you have to advect around and diffuse and things like that. But in this form, it's correct. Okay, so this is called, G is the body force, so it's a real force. Gravity, say, let's call it gravity. We're going to drop it. Let's get rid of it. And this is the stress tensor. Okay. Actually, maybe if I have time, maybe I'll talk about some of these rotor systems, so which would be fun. They're not really biological systems. There are some biological analogs involving bacteria at surfaces that are spinning each other around, and also Volvox dynamics. But there's been some really nice, interesting active matter synthetic systems that look like that. Okay, Navier-Stokes. you'd have to call the the mother of fluid mechanics the Euler Equations. So Navier-Stokes comes in next. For uniform density fluid. In that case, there's the pressure. Here's the stress tensor. It's a pressure part. And that's twice the bulk viscosity or shear viscosity against this symmetric rate of strain. So that's the classical stress tensor for the Euler Equations. So if you're dealing with any problem where you have to deal with boundaries, then you have to worry about what the stress tensor of your system is. Okay, so this is the pressure. It is not a thermodynamic pressure. It's a mechanical pressure. It's there to maintain the divergence-free condition. And this object here is the shear viscosity. So it's the price you pay by shearing a fluid. In this case, then, I have to look at div dot sigma. So if I look at the ith component again to tell you how I am doing things, then this is del sigma I del xj, sigma ij del xj. It's funny, I don't know why I wrote a capital sigma. I just don't use it, but it slipped past me. Okay, so that's my divergence. And then in this case, div dot sigma is simply minus gradient of the pressure plus mu Laplacian u. Okay. No, I just said div dot sigma. I just calculated that. Yeah. That's what I was about to write down. Yeah, that's just what div dot sigma is. Yeah, that's all. Okay, so this is Navier-Stokes. Rho du dt. And just think of rho as being a constant, just a material constant here, is minus grad p plus mu Laplacian u. And div dot u is equal to 0. Okay, so that's an incompressible Navier-Stokes system that is used for 90% of the fluid mechanics that has to do with our daily lives. Let's put it that way. Okay. Now, I just want to make a couple of comments. One, this is a initial value problem for the velocity. So I have a dynamical equation for the velocity, right? And I have a constraint attached to it, a global constraint, and that's div dot u is equal to 0. So two equations, one unknown, or rather, two equations, one which evolves, the other is a constraint, a static constraint. And that's what the pressure takes care of. That's why the pressure is in this business, is the pressure is whatever it needs to be in order to maintain under evolution the incompressibility of the flow. Okay, that's its job. So it's not like a thermodynamic thing which can be adjusted in various ways having to do with, how big your balloon is or something like that, right? So pressure can be thought of this way. It's slightly different formulation. Can be thought of as a Lagrange multiplier to enforce, I should say by whatever means necessary, the divergence-free condition. And this is a huge constraint on the nature of flows. Actually. So you never have any behavior that's like a sink, where all the velocity arrows are pointing in, right? That wouldn't be divergence free. That would be driving up the density. And the pressure will be a countervailing force. If there's a force that's trying to push things in, the pressure will push things out. That also makes fluid mechanics as a technical discipline extremely difficult, because the PDE that you have is global. Everybody talks to everybody else, and that's an important part of the way the Stokes equations behave. Is if I move a little thing over here, something there knows it immediately. It has infinite sound speed. Okay? It may decay, but you know. Eraser. So I feel kind of like Madonna with my little headset on. It's a little embarrassing, frankly. Or I'm giving a TED talk or something. It would be even more embarrassing. Has anyone in here ever given a TED talk? Will anyone admit that they've given a TED talk? No. Okay. Okay, so let's talk about boundary conditions. Let's say I have an object, looks like a wing for some reason, and it's moving through the fluid. And if I take a look at the boundary, it's got some velocity v of the boundary, and it's exerting a stress at that point onto the fluid, and I'll call that stress zeta. Okay? So consider a body. Omega. Moving through a fluid and exerting a stress upon it. Now that stress could be a stress that's a consequence of the fact that I'm prescribing its boundary velocity, or it could be that the stress is something that is causing the body to move and creating a boundary velocity. This is getting to the nature of boundary value problems that are associated with the Stokes equations. Okay, so and then here, this is a wall, a rigid wall. So let's call the boundary of this gamma. So that's delta omega. Then on gamma, we have two boundary conditions, and they're not independent typically. Two boundary conditions. One is no slip, which says that the fluid velocity on the boundary has to match that of the object. Okay? Now, there will be models of low Reynolds number locomotion where we will violate that condition, because we want to model things that are happening on a small scale that might be the action of flagella, kind of creating something like a slip layer on the boundary of an object. So we may violate that from time to time, with the idea that we could build a microscopic understanding of how that came about. So, but that's one. And another is equal and opposite forces. And so then the force, I told you, you even questioned me about it, that was the force that the fluid was exerting across a surface. Let's call that surface gamma. Then the second boundary condition is that the fluid stress, which I told you is sigma at the boundary times the normal to the boundary. So here, let's give it a normal. That has to be equal and opposite to the force or stress that the object is exerting on the fluid. So those are my boundary conditions. On the other hand, if I'm on the wall, then what I have is that u is equal to 0. Okay. Does anyone want to contest that last boundary condition? Someone who works in molecular dynamics fusses about these kinds of things. Okay. Microscopic slip layers. Okay. So those are the boundary conditions. If I had another material inside, so say that was an interface that had mechanical forces like surface tension or elasticity, then I would have a stress jump at the boundary that was balanced by whatever the surface tractions were, so to speak, but I don't think we'll be dealing with that. Oh, yeah, good question. Well, what will happen is that that also will obey this, but this is sufficient to close the problem, and you can determine what the fluid stress on the wall is as a consequence. I kind of suppressed that, but pardon? It is the case from the object. Yeah, it's just that for objects, we typically want to think of them in one of two ways. Either we're specifying a velocity or we're specifying a stress, but it's the same. Okay. Yeah. Yes. So you have to say what you mean by well posed. Okay. Yes, there is. That's right. And so so it's what's called the Navier-Stokes equations are what are called locally well posed in time. If you give them sufficiently small data in the proper sense, then you can prove that you have existence of solutions in the appropriate spaces for some amount of time. If the data is really small, you can prove that it's global in time, and you can use the kinetic energy dissipation to help you push that through. But the general problem of posing an initial value problem for Navier-Stokes and just letting it go, that's a big open problem. Right, so I see you reading Latinskaya once in a while. Yeah, so how many of you know who Latinskaya was? This is not a PD analysis. Yeah, it was a Russian mathematician, and she proved lots of very nice things. Early results on the existence of solutions to Euler and Navier-Stokes, actually. So, if the data is if the initial value for U is sufficiently small in say L2, something like that, right? Then you can use the dissipation of kinetic energy to control everything, and it will stay small. So what you're doing is you're making it small enough that viscosity is always important. You can effectively think of it as being a low Reynolds number flow, and you can't have vortex stretching to any great amount. Okay. Yeah, I could say some other things. You can derive, if you want, might be a nice little calculation to derive the dissipation of kinetic energy in a closed system like this, or in an open system, just a little calculation. Kinetic energy density in this case is 1/2 rho u squared. It's a nice, easy exercise. They're Galilean invariant equations. Of course, you break Galilean invariance of the system by having things like walls where you're specifying a velocity on it. But let me talk a little bit about vorticity, because we will have to deal with that later. I just want to deal with it now. That's because there's some interesting kind of structural similarities between things that show up in dynamics of particle systems and high Reynolds number vorticity problems. Okay, so vorticity transport, that just means take this equation and take a curl. Okay, so vorticity is the curl of the velocity. Curl kills. It's like paper, scissors, rock, but curl kills grad, right? And so in 2D, you get the answer that, oh, I should say, In 2D, the vorticity is a scalar that points out of the board. So let's say I have a two-dimensional flow in the xy plane, then the vorticity is actually that, okay? And so this we will call often just the scalar vorticity, and it obeys the omega dt is 0. Oh, vorticity transport, geez, for mu equal to 0. Let's set the viscosity to 0. Why did I do that? I don't want to do that. Let's call it that. This object is also called the kinematic viscosity. Okay. So we just have an advection diffusion equation for the vorticity. If I took the viscosity to 0, I went to the kind of inviscid limit, then I would just have conservation of vorticity, which I had talked about way back before. In 3D, if you're not really following while I'm doing this, I just want to get it down on the board, and then we're going to leave it for a while. Okay. In 3D, you have a fully vector vorticity, and it looks like this. Has that form. And when you go to the high Reynolds number or inviscid limit, this term will drop out again, and you have this weird equation, okay, that shows up. And it turns out that this is, just like this is expressing a conservation law, if I set that to 0 over here, this is as well, and it's called the result of Cauchy, which I probably will not show you unless someone demands to see the result of Cauchy. Then I have to talk about Lagrangian frames and all this kind of stuff because it's a little weird. Okay, I just wanted to write that down for no other reason. Oh, but let me say, since Wen asked this question about well-posedness, this is the root of all evil in understanding this equation. It's this guy right here. And this is the term, if you ever hear about vortex stretching, this is the object that causes vorticity to stretch, right? If it weren't here, then it wouldn't, obviously. So if it's there, it must. But so if I have a vortex tube, it's been shed by a bird, say, just to make it relevant to this lecture. I have some tube of vorticity that's shed behind. It's in a straining flow. That straining flow gets encapsulated into this guy, and it causes things to stretch out. Oh, speaking of straining flows, I can rewrite it this way. Okay, symmetric rate of strain times the vorticity. And you do the same thing. If I rewrite this grad U in terms of E and W, right, then the W part is omega cross something. But it's omega cross omega, so it's gone. So the only thing that ends up showing up in the stretching term is the symmetric rate of strain. It's something that's like that ellipse I drew. This is the guy that stretches stuff out. It's called the self-stretching term. Okay. Yes, you do. If you're in an open flow, you typically will say that the velocity decays to 0 at infinity. That's another reason why I'm avoiding 2D problems. There are irritating things that happen in 2 dimensions for the Stokes equations. Right? How many people know about the Stokes Paradox? Yeah, about a third of you. If I have a 2D, here's why it's so irritating. You shouldn't, okay. I won't preach against something, but if I have a 2-dimensional Stokes fluid and I exert a force on it, a finite force, it will cause a logarithmically divergent velocity field at infinity. That doesn't happen in 3D. Decays like 1 over r. So I try to avoid that. How am I doing on time? 25 minutes? Okay, great. Oh, I didn't want to erase that. Now we talk about our canonical dimensionless parameter, the Reynolds number, and our canonical physical problem of a body moving through a fluid at a speed u. Now I just want to set up the different ways in which you scale the problem to move into different limits. So there's my system. Okay, so here's my problem. That's a bird. It's got a size L. And it's flying at a velocity u through a fluid. And this fluid has two material coefficients. It has mu and rho. Okay? That's what specifies the fluid. That's what specifies the body. So let's just make everything dimensionless on that length and that velocity and the consequent time scale. So now here on the right-hand side, x and u are now dimensionless variables. And time, we'll do it by the natural time scale there. It takes you to go, the time it takes to go one body length. And the pressure we will leave with a as yet undetermined pressure scale. Okay? The main thing you have to remember about pressure, again, is that no matter what kind of limit of inertial forces or viscous forces you are going to, you cannot scale out the incompressibility condition. It scales itself in a way that keeps it in the game, so you have to kind of respect that here. Okay, I stick that into the Navier-Stokes equations, and I will get the following. The Reynolds number times du dt is equal to the pressure over mu ul, pressure scale over that, with a minus sign grad p, plus a bare Laplacian of u is equal to 0, and div dot u is equal to 0. Okay? So I want to choose a pressure scaling in two ways to emphasize what physical regime I want to look at the equations in. Okay? So in the first, let's say we're looking at the case. I should define the Reynolds number again. I just did it on that slide before. That's rho ul over mu, or ul over nu, that kinematic viscosity. Okay? So let's say I want to look at the case. Reynolds number is much bigger than 1. Okay? Which means I'm going to want to scale away that Laplacian term, the viscous forces. So what you do is you choose the pressure scaling to be the Reynolds number, because it makes sense, u over L. And then what this turns into, now any of these spatial scalings, as long as you treat all the dimensions in an isotropic way, you never can rescale the divergence free condition in any way that's meaningful. It just stays div dot u is equal to 0, because u goes with x, v goes with y, w goes with z. Right? Okay, so then in this case, what we will get is du dt is minus grad p, and I could rewrite it. All I did is I just made sure I had a Reynolds number sitting on the gradient of the pressure, because it's there to take the divergence free condition. So that's the way I'll scale it in this case of a high Reynolds number. And now if I take the Reynolds number to infinity, at least in a formal sense, I remove the viscous response to flow. Okay? Okay. Now, so what I end up having is just the Euler equations. How many of you have studied the Euler equations? About half. All right, some good part. How about boundary layer theory? Ah, excellent. So now what I end up with then is just the Euler equations. And I have this vorticity transport equation, but just ignore that. It's just my youth. I'm compelled to write it because that's where I started my career. Back there with Cauchy and Euler. Okay, so now what's wrong with this limit? Yes. Oh. What was the question? Okay. So the problem with the Euler equations is that if you're trying to look at a large but finite Reynolds number flow, you still have that no-slip boundary condition for any finite Reynolds number, right? If I have flow along a wall, then the velocity of the fluid has to be 0, okay? So as I take the Reynolds number to 0, then, to infinity, the length scale over which the velocity moves from being something in the free flow to being something at 0 at the wall scales like a square root of the Reynolds number, 1 over the square root of the Reynolds number. So the problem with this limit, I call this formal somewhere, and that's because you have an inconsistency with your boundary data in this limit. Inconsistency with no slip condition. In fact, usually the no slip condition is just replaced by something. If you're ignoring viscous effects altogether, you say that you have a no penetration condition, but you can slip along the wall. Okay, and it's this problem that gives rise to this huge edifice of fluid mechanics called boundary layer theory. Okay, which really started with Prandtl. Okay, but it has lots of interesting aspects to it as a fluid mechanics problem, and does show up when you have to think about things like flight of organisms at high Reynolds number. You can treat the outer flow away from the swimming fish essentially as a kind of inviscid flow, but near the surface you have to account for viscous effects in producing vorticity and things like that. Okay, the other limit I'm just going to drop that Reynolds number. So Reynolds number much less than 1. In this case, we will just eliminate this term by setting the pressure to mu u over L. In that case, I just have Reynolds number du dt, and now I've kept the pressure and the viscous forces in perfect balance. Okay? And now as I take the Reynolds number to go to 0, I get the Stokes equations, the famed Stokes equations. And here I will mostly, unless you see me put a viscosity into them, I will be dealing with them in a dimensionless form. Okay? Now, what can we say about Stokes? So this is if you're dealing with organisms swimming around in water, small organisms where the Reynolds number is very small. Reynolds number is around 10 to the minus 5 for swimming bacteria. It's around 10 to the minus 9 for something moving inside of an embryonic cell. You had a question? The mass of the fluid. Yes, that would be fair. Yeah. In fact, I have friends that think about it in exactly that way. A fluid that is light and a fluid that is heavy, and it drives me crazy. Yeah. I can't. Very eminent people in fluid mechanics. Okay. Okay, so here you don't have any problem with inconsistency with boundary conditions because I've left the highest order term in the partial differential equations, the Laplacian. Again, I keep the no subcondition. There are some other complications off at infinity if you want to worry about them too much, but we will not. Okay. Some properties of the Stokes equations. One, it's a set of linear constant coefficient PDEs. Okay? I will demonstrate to you, if you don't know this already, that philosophically it's the same as though I were just solving a Laplace equation. Okay? Laplace equations you solve as boundary value problems. This is, as we call it in the business, a BVP, a boundary value problem. I determine everything by saying what goes on the boundaries, where I exert velocities or exert forces or something. That makes flows. 2. Let's say I take a divergence through this first equation, right, the F equals ma. I switch the divergence with the Laplacian. I apply the no-slip condition. I have Laplacian P is equal to 0. That's a very useful fact when you're building solutions to the Stokes equations, is that there is a harmonic problem in here immediately, and that's that the pressure in the absence of any external force in the system is harmonic. Okay? Let's say I take a curl. Curl kills grad. I interchange it with the Laplacian. I remember what I'm calling the vorticity. This gives me the Laplacian of the vorticity is 0. So the vorticity is also harmonic. This has so much structure to it, right? Everything is just kind of like a harmonic function or something like that. So vorticity is harmonic. 3. The divergence-free condition implies, in most instances, that there exists a stream function, psi, such that U is curl cross psi. Okay? And what this means, actually, if you work through it, is that the bi-Laplacian of the stream function is 0. So it's actually this last thing, this last statement that is the fundamental nature of the Stokes equations, is that it's a biharmonic, a homogeneous biharmonic problem. Okay? If I pose, what kind of data does a biharmonic problem need? It needs 2 bits of data on the boundary, not just 1, as though I were solving a harmonic problem. Am I going over? No, okay. So Laplacian of something equal to 0 means I need to specify boundary data of some sort. If I have a bi-Laplacian, I have to give 2 pieces of boundary data. Okay? So if I say that I have a boundary condition on the velocity, okay, say in 2D, that's 2 bits of boundary data. One is d phi dn, the other is d phi ds along the boundary. Arc length derivative, normal derivative. That's what will, in 2D, that's what will solve this problem. Okay, so you have the right amount of boundary data in terms of velocity to solve this biharmonic problem. Okay, and then construct the velocities. But this is, you know, I'm not going to write all that down, except I just want you to remember that as like a little fact that you've stored somewhere, that the Stokes equations are fundamentally the same as a biharmonic problem to solve. It's like 2 Laplacians. Okay. I have a few more minutes. Man, I'm really like flying along. I have to go through my notes. Or maybe I'm going backwards. That'd be kind of a disaster. Okay. Okay, I was going to say one more thing. So I have these homogeneous constant coefficient equations. Let's say I have a body moving around, squiggling, right, inside of a Stokesian fluid. And how does it interact with that fluid? This is a very important point. Consider an organism. Consider a bacterium. Let's make it specific. Moving freely in a Stokesian fluid. See, the more incomprehensible my writing becomes, I try to make it more florid to make up for it. Look more grandiose, less readable. Okay. So that bacterium has a mass, m sub bacterium, right? How does its center of mass move? So it has a mass, and let's give it a center of mass xc. Let's say it's a uniform density thing. Its density match is more or less the same as water. Now what I have is mb xc double dot is what? It's moved by the sum total of all the fluid forces on the beast, but those are forces of stress. So this is, it's called the surface of the bacterium, gamma sub bacterium. ds, there's a stress tensor of the fluid, dot the normal. Okay, so that's how the bacterium moves. But in this Stokes limit, what did I do? I chose the pressure to scale that way, right? Sorry, let me just recover something. Yeah, good. So in this Reynolds number, low Reynolds number limit, the sigma, because of the way I scaled the pressure, the sigma went to mu u over L, and that's the dimensionless guy, right? That's how I scaled the whole, because I scaled both the viscous stress and the pressure stress the same way. I just eliminated the pressure scaling altogether. So if I make this thing dimensionless, then this is, let me just write it down. Good. So dimensionally then, this is mb u squared over L xc dot dot. There's an L squared that comes from the ds, integral over gamma b ds, and then I have a mu u over L mu u over L sigma dot n. So I just scaled that first equation. And what it gives you is the following. It gives you Reynolds number times mb over mf xc double dot is the integral of the dimensionless stress over the surface. And this mf is rho L cubed. It's the mass of the displaced volume of fluid by the beast. Right? It is a beast. Very Old Testament. So the point is that because it's living in this low Reynolds number world, it inherits a scaling, and it's driven by fluid stresses. It inherits the scaling that I put in for the stress tensor. And I end up with a Reynolds number here, just like I did on Reynolds number du dt before I took it to 0. It scales in the same way, except that there's this cost that I have a ratio of masses. That's essentially 1 for a bacterium. So unless I have a really heavy particle relative to the fluid, this term stays small. Okay, so then in this limit, again, where Reynolds number is much less than 1, I take the limit. This gives me that the force, which is acting on the bacterium, the dimensionless force in this case, is 0. Okay, so anything that swims freely, in the sense that there are no externally imposed forces or torques, in a low Reynolds number fluid that is not massively mismatched in its density from the fluid, moves under a condition of 0 force, not in time average when we're thinking about flight of birds, but instantaneously at every time. So that's a nice constraint in the low Reynolds number world. Each little unit is swimming around under conditions of 0 force. It's also the case that the torque, by the same argument, that must also be 0. So low Reynolds number, freely moving objects swim, they propel themselves, but they have to under the constraint that they have 0 total force or torque. So when you see something like a spermatozoa swimming along by pushing waves back, it's doing two things. One, it's violating the reciprocal theorem of Purcell by having a directional stroke, which we'll talk about next. The second thing it's doing is it has a long, skinny object. And that long, skinny object has different drags depending on what direction you're pushing it. If I have a long, skinny thing, I move it like this. It has half the drag than if I move it like this. It's that drag anisotropy that overcomes this 0 force condition for getting around. It's what lets spermatozoa get around, is by having different drags in different directions. Total force is 0, but that drag anisotropy will lead you to have a velocity that lets you move around. Okay, I think that's a good part to stop. So that's some of the basic of Stokes. Next time I'm going to talk about, we'll get to, at the end of the next lecture, we will get to some things that have to do with swimming, probably well before the end. But I'll introduce you to some about singularity methods. Yes? Yeah, so there is a quandary that if you're really going to look at the size of inertia off it a long distance away, you need to include some effects of inertia. Yeah, but that's, you can get away pretty well without ever worrying about that. Well, the Stokes equations by itself are completely fine. If you look at the consequences of having moved something in a fluid at low but not zero Reynolds number and off maybe going on infinity, you might have some difficulties. Okay. Oh.